Today, we start part E, selection problem and recursion tree, part 2. Actually, because in part D, I spent some time to discuss 6 homework 1 questions. So I couldn't complete the planned material, so I moved to this part. So we will complete the remaining 2 parts left from part D. But first, I want to discuss selected questions from comprehension questions, Module 1, Part B, and Module 2, Part A and Part B. So, yeah, I select those questions a little harder relatively for you to understand. Yeah. All right, so let's look at these questions. The first one from Module 1, Part B, question number 5. Yeah. All right, so here we are given a polynomial. Is it possible that one can find a special case, not a general case, a special case? So you can imagine any possibility, you can get that special example, such that the number of multiplications to evaluate this point is less than 4. Yeah, because by the owner's rule, we need to use 4 multiplications. Yeah. But that's for the general case. Yeah. Special case, we may have some special structure, we can take advantage. Some special polynomial, we can, oh, what's that? Yeah. Yeah. So we can give some special structure. And by taking advantage of the special structure, we can reduce the number of multiplications. For example, here, let me just give you one simple example. All right. P of x equals 1 plus x squared. How about that? So you can expand it. If you expand it, you will get a polynomial of degree 4, right? Yeah. So square degree 4. So that will be a special case of this general expression. Yeah. But think about how many multiplications do we need to calculate this polynomial? We can take advantage of the structure. Okay, yeah, all right. So let me do it. First, calculate the polynomial inside the parentheses. How many multiplications do we need? 2, right? Because by Horner's rule, the degree of the polynomial, that's 2. Right? That's 2. Yeah, we need, yeah. All right, 2 multiplications, we can find the value inside the parentheses. Okay? Yeah. Suppose that is y. Y times y, another multiplication. 1 plus that 2, we get a 3. Less than 4. Yeah. So that's the way we can get the number of multiplications less than the result from the Horner's rule. Yeah. All right, so that's the question number 5. Number 11. Yeah, this one, the answer is false. Why? Let me explain it. No algorithm can be out because one can always improve given algorithm. First, when we talk about improvement, the improvement should be significant. Otherwise, we don't treat as an improvement. Okay? Okay, improvement should be significant. Significant with respect to the growth function. If you just do some minor, marginal, small, yeah, so that may not be significant improvement. Okay, yeah. So then, if we use the growth function concept, when we talk about improvement, you should improve the growth function of your algorithm. Okay, growth function of your algorithm. Then we can say significant improvement. The order of the growth function should be reduced. Then we can say you improve the algorithm. If the order is not reduced, then we cannot say you do significant improvement. Yeah. All right, so we understand the meaning here. Then, no algorithm can be optimal. It is wrong. Why? Because we can prove this algorithm, its growth function cannot be reduced. We can prove it by exploring some special property of the problem. We can do that. We can show the optimality. Nobody can improve this algorithm by any method. Yeah. We have one example, minimum value problem. Find a minimum value problem. Okay, yeah. In that one, the number of comparison we use n-1. And this actually we prove not just growth function cannot be improved. We prove this number cannot be improved. This number cannot be reduced. This absolute value cannot be reduced in our proof, in our argument. Yeah. So if you go back, look at our proof. Yeah. So this is, we can do it, right? Yeah. So this algorithm, our algorithm is optimal. Yeah. Because we can prove it. It is optimal. Nobody can do further improvement. Yeah. Even we do not say significant, even marginal improvement, minor, slightly little improvement cannot be done for this particular example. Yeah. All right. Next question. CQ2A, question 9. Yeah. For this one, why I select this one? Faster. Faster, that means the growth rate lower. Then we say faster. Okay? The answer is this one. Why I select this one? Because based on my experience, when I gave this question to my students before, there are pretty big percentage of the students, they selected this one. That's wrong. The reason they select, they're based on their intuition. Yeah. Because many people, when they make decisions, they're based on their intuition directly. This one, pretty much against your intuition. Yeah. So this one, because the reason, when you see 1.01, it is a very small number, very close to 1. Okay? 1 plus 0.1. That small number you raise to nth power, right? Nth power. It looks like, based on your intuition, it looks like it cannot grow too fast. Okay? So that's one side. The other side, n you raise to 100th power. Then you can imagine this function can grow very fast, right? Yeah. So based on this kind of, intuition, that's the reason many students pick A. The answer is B. So now I need to explain why the answer is B. Okay. Mathematically, we need to use math to help us make the decision, not, to help us fight against the wrong intuition. Yeah. All right. First, from the math, tells us even 100 is a relatively big number, n to the 100. It is a pretty big power function, right? But it is a polynomial, right? It is a polynomial, all right. Then this function, we can write a to the n, right? And a greater than 1, right? Yeah. And this is an exponential function. Exponential function and a polynomial function. Yeah. And we know exponential function dominates polynomials, all the polynomials. Okay, yeah. And in our module 2, part A, yeah, so we proved one result. Yeah. You can go back, find the notes, you can see n to the dth power belongs to little o of a to the nth exponential function with a greater than 1. D is a positive number. Our 100, can we use 100 as the D? Any positive number. Okay? Even 1 million, we can use 1 million or 1 billion. It is still a polynomial. Still little o, what's the meaning of little o? Okay? Little o means when you take the limit, n goes to infinity, n to the dth power, you compare it with exponential function, it is 0. Which one dominates which one? So you can understand easily, right? When n is very large, right? Yeah. So that's the answer of this question. Next one, 2 questions. The 2 questions closely related, so I want to put them together. So I hope you can understand the reason behind it. We compare efficiency of 2 algorithms through their running time complexity functions, f of n and g of n. We know the limit of the ratio of these 2 functions equals a positive number, c, okay, constant. Then we can say that these 2 algorithms have the same growth functions. Yes? Yeah, that's true. So why? Yeah, because, so you can think about when n is very large, the ratio close to some constant. Yeah, so if we use the asymptotic notation, we can write f of n belongs to big theta of g of n. So in this case, they have the same growth function. Okay, yeah. Theta, big theta. So here you can see the same growth function. Here we can, the condition, same growth function condition corresponds to one function is in the big theta of another function. We can understand in that way. Okay? Yeah, we can understand in that way. All right. So with that, then we have another function, another related question, similar but different. It says, all right, yeah, 2 functions, f of n, g of n. If these 2 algorithms have the same growth function, we change the order of the conditions, okay, have the same growth functions, then we have this limit. The answer is false. Yeah. Even they have the same growth functions, this just one of the possibilities, right? One of the possibilities. And there are other possibilities, right? Other possibilities. Okay? So you cannot say this must happen. You cannot say that. Yeah. All right. So here I may like to draw a diagram to show you, why is that. Suppose this big circle, I represent the set of same growth function. Yeah. So this case, the set of that case. All right. Then this ratio limit equals positive constant. That's just the subset inside a circle. Subset. Yeah. We may have other places in that set. Yeah. That means the condition for this one may not be satisfied, but we can have other conditions satisfied. Yeah, right? Yeah. The counter example I give you in my video in my class, I give it to you. Okay? Yeah. For example, so here I can write it again. Ratio of two functions. Okay? All right. 2 plus -1 to the nth power n squared plus 1. Right? Yeah. Another function. Yeah. I need some room. 2 minus negative to the nth power times n squared minus 1. These two functions, when n goes to infinity, there is no limit. Okay? But they have the same growth function. That's the counterexample. Yeah. That's the counterexample. Yeah. All right, so compare these two questions. Try to understand. Yeah. All right. Then the last two questions. The first one. Which one grows faster? Grows faster, right? Yeah. Grows faster, that means the value should be larger, right? Grows faster. Not the algorithm faster. The function grows faster. Okay? Yeah. This function. Not that. Yeah. Why? All right. If you look at the limit, when n goes to infinity, log of n equals infinity, right? It's easy to see that. Log function also goes to infinity. But what's this? What is the limit of this function? When n goes to infinity, n to the 1 over n goes to 1. Goes to 1. Yeah. If you look at your homework, so our question number 24, remember in my video I explained we can show, because we need to use the L'Hopital's rule, so we use the continuous variable x. We show equals 1. Yeah. L'Hopital's rule. So remember how did we show it? Using e base. Okay. So then natural log of x to this one. Same thing. Yeah. So then, because natural log e to the natural log x over x. Okay, this one. Okay, yeah. So then you just do the limit of that one. This limit goes to 0. L'Hopital's rule goes to 0. Then this equals e to the 0. That is 1. Okay, so remember, yeah, that's part of our homework question, HW1 question 24. Part of it. Okay, yeah, related to this one here. Yeah. All right. The last question. Last question, in one of my videos, I explain it. Yeah. I hope you can get it. Yeah. So here I just do it again. So if some of you are not familiar with what we did in that video, so here I just repeat it. All right. The formula we use, a to the log base a of n equals n. So this is the formula we use. Condition, a greater than 0, a not equal to 1. Yeah. Keep in mind the condition. Then we can use this formula. Otherwise, we cannot use this formula. Okay? All right. Now, so let's try to simplify this function. Because this function, it is very hard to see, to compare with this function directly. It's hard to compare. Okay? We want to write that function as n to some number. Yeah, let's say b, some number. Then we can compare this b number and the exponent of this function, that's 1. Which one larger, which one smaller? Yeah. So you can see which one grows faster. Okay? So let's do that part, that step. Remember, we need to use the same base. Yeah. Same base. Exponential base and the log base must be the same. Here, different. Exponential base 3, log base 2. So we need to do conversion. How do we do the conversion? I showed you before, so now I show you another time. 2, we need to convert to the base. Base 2, okay? Base 2, using the formula, this time a we take 2. We can use 2. N equals 3. How about that, right? Yeah. 2 log base 2 of 3. Right? So can you see this? Apply that formula directly. So you have that. All right, after that, 3 to the n equals what? Equals 2, 3 to the, hey, yeah, all right. So this, by the property of exponential function, equals multiplication, the product of these two numbers, right? Yeah. Product of these two numbers. Okay, all right. Yeah. Is this number we can treat as that b? Constant b? Can we make this constant b? Right? Yeah. Yeah. So we can make this equals 2b times, right? Yeah. Then, using the log property, can we write that as n to the bth, a property of log function? Yeah. All right, now same base equals n to the bth power. N to the bth power. Okay, so what is that b? B, based on our assumption, b equals log base 2, 3. Now you compare with 1. Yeah, that exponent 1 here. Which one is larger? Because 3 bigger than 2, right? 3 bigger than 2, so it is larger. We know log base 2, 2 equals 1. 3 greater than 2. So 3 greater than log base 2 of 2, that is 1. All right, so this b greater than 1, so that means this function grows faster. Grows faster. Now, I hope you can master this method. Yeah, So we use a lot of formulas, a lot of properties, logarithm, exponential functions. You need to be familiar with all these formulas. Okay? Yeah. So I will find a chance to let you do some practice. Yeah, probably, because the next chance should be in your test number 1. Yeah. Test number 1, I will announce the time quickly. Yeah. You have, near the end of this month, about 2 weeks from today, about 2 weeks from now. Yeah. So right now, it's the Monday. Yeah. Monday. Yeah. Yeah. But I will use weekend, I plan to use 3 days, give you 3 days for your test 1. Okay? Saturday, Sunday, Monday. 3 days for your test 1 at the end of this month, about 2 weeks from today. Yeah. All right, so we finish this part, E.1.